So now we'll discuss state function or point function and the path function. So at first we'll discuss the state function. So a state function or a point function is a property of a system whose value depends only on the state and does not depend on which path is taken to reach that specific state. Okay. So some examples of state functions are the pressure, volume, temperature, entropy, internal energy, etc. Now in contrast to a state function, what is path function? So a path function is a property whose value depends on the path of the process which is taken between the initial state and the final state. Okay. Some examples of path functions are work and heat. Now we can use the indicator diagram to understand state function and the path function better. So suppose here we have an indicator diagram whose vertical axis we have taken to be the pressure axis and the horizontal axis is volume axis. Okay, and this is suppose state 1, this is state 2. Okay, at the state 1 the volume is V1 and its value is suppose 2 meter cube. Okay, we are showing only the volume, not the pressure. And at state 2 the corresponding volume is V2 whose value is suppose 5 meter cube. So we have to reach this final state. Okay, we want to reach the state 2 where volume is 5 meter cube. Okay, so initially the volume is 2 meter cube. So it is obvious that we have to go through some process such that its volume increases. Okay, so the system has to undergo some process. Now there can be various processes to increase the volume. So one of them can be an isothermal process. Okay, so in case of isothermal process, if we express it on an indicator diagram, then it will, the PV indicator diagram, it will look like this. Okay, so in this way. And the other process we can go through, suppose, so the first one, suppose this is process A. So the process A is an isothermal process. Okay, and another process you can take is suppose the first an isobaric process, then an isochoric process. Okay, so this is process B. So process B is a combination of first one, this is isobaric process, pressure is constant, isobaric process, and then this one which is an isochoric process, the volume is constant. Okay, so here you see the finally, after we have gone through two different processes, the final state is state 2 where the volume is V2 equals to 5 meter cube. So as we know that volume is a state function, and according to this definition, a state function is a property of a system whose value depends only on that state. So the volume V2 equals to 5 meter cube, this value depends only on the state 2. It does not depend which path is taken to reach that state. So for the second part of the definition, you see its value does not depend on which path is taken to reach that specific state. So initially we are at the state 1 and we want to reach at a volume V2 whose value is 5 meter cube. Okay, and the volume is a property or state variable of the system. Okay, so and the volume will be 5 meter cube when the system at suppose state 2. Okay, so we can take various processes to reach this volume. So as you can see, this volume V2 equals to 5 meter cube is only depend on that state 2. It does not depend which path is taken to reach that state. So at first we have taken some isothermal process and then some combination of isobaric and isochoric process, but no matter which path is taken, which path of process is taken, this value will always the value of the volume at state 2 will always be 5 meter cube. So the volume is an example of state function or point function. Okay, now in contrast to the state function, we know a path function will depend on the in the path of the process, and one example is work. Okay, so here suppose we know for the thermodynamic system, work is expressed in this way: P dV V1 to V2. Okay, so suppose this is state 1, okay, and this is state 2. So suppose the system make transition from state 1 and state 2 by some process whose path looks like this. Okay, so suppose initially here the pressure volume is V1 and here the final volume is V2. So suppose this is any point on this path or curve where the corresponding pressure is P and the volume is V. Okay, then suppose at that point if we make a very small change dV in volume, then system has to do some work. Either work will be done on the system or done by the system. Okay, no matter what, the work done will be dW equals to P dV. Okay, so what is the total work done in making the transition of the system from state 1 to state 2? It will be all this sum of all these strips. Okay, small pdv to pdv, pdv small dw. So the total work done dw will be integration pdv, as this integration is over v, so it will be the initial volume from v1 to final volume v2. Okay, so for thermodynamic work done, the work done is the area under the curve, or you can say curve or path of process. You know, this is path of process or process path on PV diagram. Okay, so this is equal to the work done by the system. So if a system undergoes through a process like this, and this is the path of the process, then the area under that process path will be equal to the work done by the system or on the system in that process. Okay, so now if we take this similar two cases where the volume, you see, volume was independent of the path which was taken. Okay, but now you'll see that the work done in the two cases will be totally different. Okay, so the first one is this, that we have some isothermal work done, isothermal process. The path of the process is like this. So this is state 1 and this is state 2, and the combination of isobaric and isochoric is like this. So if we draw these two curves separately, then so this is the isothermal one, and then we have the isobaric and isochoric one. Okay, so this is state 1, state 2, this is state 1 and state 2. Okay, so as we know, the work done will be the path under the work done will be the area under the path of a process or the curve. So here, what is the area under the curve? So area under the curve is this one. Okay, and for the second process, So this one process A, process B, so process A, and this is process B. Okay, so in case of process B, what is the area under the curve? This is the area under the curve. So it is very evident. So these two areas are completely different from each other. So so if you could calculate these two areas, you will see that they will have different value. So thus work done, thermodynamic work done is a path function, that is they will depend on which path is taken. Okay, so there is a system, it goes through some process and some work is done. Okay, so that work done, it will depend on which path is taken, okay, between the initial state and final state. Okay, so a path function is a property whose value depends on the path of the process between the initial state and final state. In both the cases, you see the initial state and final states are same, but the path which are taken to reach from the final state and the second state are different. Okay, so the work done being a path function, their value will also be different for these two different paths taken. Okay, even though the initial and final states are same. So similarly, heat is also a path function, but heat is a path function cannot be shown by a pressure and volume indicator diagram. We have to use some other diagram. Okay.